In the previous lecture, we discussed about the limitation associated with the Drude model. In Drude model, we consider electron to be classical particle. So it follow Maxwell's statistic. This has led to the underestimation of the thermal velocity and overestimation of heat heat capacity. Later, Sommerfeld made the changes in the Drude model, and this time he assumed or model electron as a quantum mechanical particle, which follows Pauli exclusion principle. We also discuss about the energy associated with a string. We know if there is a, let's say, a string, if there is no restriction on this string, then it can take any value. But if these two ends of this string are bound, then in that case this has led to the discretization of energy. In that case, the wave vector is is n pi upon a. This in turns will lead to the, we know the energy defined h square k square upon 2m. So this will lead to square I square upon 2 ma. Right. So when we put the restriction on the movement of the skin, this has led to now the k vector can, or wave vector will take value associated which depend upon value of a. This in turn means that energy is not continuous; it will take only those values which correspond to value of a. Now let's discuss further on this concept so in the light of quantum mechanics. For this, we will use Schrodinger wave equation. We know the Schrodinger wave equation described as h square by 2m d square phi x on dx square, where phi is the wave function, plus Vx, V is potential energy, equal to E of phi x, where this is kinetic energy, this term is potential energy, and this is total energy. So now let's consider for the case first. For free electron, here the free electron means it is not experiencing any kind of potential. It is very far away from the solid, so it is not has any kind of interaction to a potential, which means V of x will be 0. Right. So this the modified s, if you put this value in the Schrodinger wave equation, then we will get E of phi x. Rearranging this equation, so what is this equation is showing that a double differentiation of a function is coming out with that function itself again back and with some constant, which but that means that solution of this equation will have trigonometric form. So the solution of this equation will be something which consists of trigonometric functions, a, which is any constant, cos of k of x, plus b sine k of x. So if we it will be of this form. If we double differentiate this, we'll get, and we will get minus k square and a kx plus v sine p of x. So it will be phi of x on v of x square equal to minus k square phi of x. Right? Now, if we compare this equation A and this equation B, which means k square is actually 2me upon h square. If we rearrange it, we will get expression of energy, which is E square, which we actually seen in the case as well, k square upon 2m. Now here in this value, k can take any value, which means E can take any value. And if we plot this curve, value and this corresponding value, so if k can take any value, so if k can take goes any value, it will corresponding there will be value of E, and it will be equation of a parabola. Right. This is the case when there is no restriction of electron is free 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 electron. It is not explaining any kind of a potential. Now consider case 2. In case 2, the case 2 is for the bound electron. Bound electron, like bound electron or confined electron. In this case, we consider electron to be in a potential well, and the potential well is very deep. And basically, we are putting a restriction on the electron movement. If it is center minus a and a, suppose electron is in a potential well at zero potential, and it's very deep, and it's so deep that electron cannot escape this potential well, which means probability of finding a particle electron outside this ball will be 0, and that in turn means that with the boundary condition, the probability of finding an electron at this boundary at x equal to a and x equal to minus a will be 0, which means phi of a will be 0 and phi of minus a will be 0 for the condition of the bound electron. And of course, in this potential, the potential also experience it is also 0. Now, from the Schrodinger wave equation, coming back to the Schrodinger wave equation, now this term is 0, and rearranging this equation as we did previously, so it will be d square phi of x equal to d of x square minus 2m e upon h square upon phi of x, right? This time we call it 1. Now Again, this solution of this kind of equation where double differentiation giving back the function itself back will be of form trigonometric form a of cos of k of x plus b sine of k of x. Right, now we will use these boundary condition to apply further, like phi of at phi of a equal to 0 is a cos of k of x plus v sine k of x 0, and phi of minus a will also be 0. This time it is k of cos k of x minus v sine k of x. Now from these two equations we will have 2 of v sine of k of x equal to 0. Now this is constant, so of course this cannot be 0. It means these terms will be 0, and for this term to be 0, it means k of x must be integer multiple of pi. So k of x has to be n pi. Sorry, here it will be k of a. All these equations will be k of a. K of a has to be fn. So which means k has to be n pi upon a, and the corresponding energy will be h square n square pi square upon 2m a square. Right, now what this has led to us to the, if we plot the energy and versus k plot, we will see how it is modified if you put the restriction. This section is k and this is energy E 0. So this is pi by a and this will be minus pi by a. This will be 2 pi by a. Similarly, this will be 2 pi by a in minus sign. This is 3 pi by a. Similarly, it will be minus 3 pi by a. With this, at this value, this is will be the energy values. I will just put 0. This corresponding to energy is 0. So which means that at corresponding to k values, it is not a continuous function but a discrete. It has certain value. Earlier it was continuous, it was taking all the value. Now it has led to the quantization of energy or discretization of energy. This was the case for the bound electron, and for the case for the electron which are nearly free, like they are not very far away from sample but within a sample, they are restricted within a sample. Let's say this is a sample of length This is sample of length L, and electrons of course cannot escape this outside this solid. So this will means K of n will be n pi upon L, where L is much greater than A. What does that simply mean? That if L is very big, K will be very small. So it means the energy spacing between energy will be very closely spaced. So energy spacing between them will be very less as the L or A is increasing or L is decreasing as we go for the very small dimension. The energy separation between the different energy level will increase. Let's proceed further and discuss the concept of density of state. This is defined as d of E, density of state. It actually tells about the number of state in energy range E to E plus E. This tells about number of states in energy range E to E plus D. And also just to introduce Fermi-Dirac distribution, which we discussed previously as well. Fermi-Dirac distribution, which is defined as f of t. This will be useful in this and also in coming lectures. What it tells about the probability of occupancy. We say the probability of occupancy of a particular energy of a state is 1 up to until Fermi energy, beyond which it is 0. This is for the temperature when temperature is 0 Kelvin. Okay, so it tell about only the probability. It doesn't tell about whether it will be occupied or not. For electron to be there has to be state. It could be that for lower energy there it has more density of state. Here it has less density of state, more spacing in between the energy. So to actually find out density of occupied state, this is what will be more interesting. Density of occupied state is actually what is defined as n of E is actually what is the density of state d of E, and if we multiply it with the what is the probability that this state is actually occupied of E. So this actually will tell us what is the density of occupied state. We called it equation A, right? And now, as we also discussed previously many times, energy is h bar square k square upon 2m is actually equal to pi square when it is electron confined square pi square upon 2m a square. This is equation B. Now, in 3D space, or we can describe n square is actually equal to n of x square plus n of y square plus n of z square. If you use this put this in equation, then energy E becomes h bar square pi square upon 2m a square n of x square plus n of y square plus n of z square. Now, if we look closely to this equation, for a given energy, for a particular energy value E, this is will be constant, of course. H bar is also constant, pi square is also constant, 2m a square is also constant. So what we are getting is nx square plus ny square plus nz square to a constant value, which actually is a equation of a sphere. So what it will be? This will tell this is actually come out to be equation of a sphere in a quantum number space. Like now, the total number of cloud states up to energy En. Up to energy En, it will be actually the volume of the sphere, considering only the positive value, positive sphere, positive coordinate. So it will be n of p. Positive coordinate is basically will be 1/8 of the volume of the sphere, because we are considering only the positive value. So it will be the volume of the sphere will be 4/3 pi n cube, right? Or eventually what does that mean? Means 1/6 pi n cube. Let's say this is equation C. Now from equation C and equation B, from equation C and equation B, right? But it will be n of E, n will be actually equal to pi by 6 bracket 2m a square upon h bar square and pi square to the power 3/2 h bar. So E will be 3/2. So we are writing it, n of En is actually pi a cube by 6 2m upon h bar square pi square to the power 3/2 and to the power 3/2. So this will be equation D. Right now, another way of describing the n of En, or density of occupied state up to energy En, will be n of En will be actually integrating density of integrating up to En density of state. Sorry, and D. This is another way of describing density of occupied state up to energy En. Now, if we differentiate this equation with respect to energy, what we will get? D of n of En on D of E, right? Then D of E will be actually, if we differentiate this equation, but it will become pi a cube upon 4 2m upon h bar square pi square to the power 3/2 exponential 1/2. So we have two equation. In one equation, it is varying as a e to the power 3/2, and d of e is actually e to the power 1/2. Now, what does that mean? If you plot this curve, how it will look like. This side is energy, and this side is density of state. So how it will be? It will be something like this, because it is e to the power 1/2, and we also described previously also Fermi-Dirac distribution. Which tell about the probability of that state being occupied. Right? Here it was 1, here was until E of S. This was for when T was 0 Kelvin. Now for the other temperature, let's say T equal to T1, some other temperature. And we earlier also discussed, so we change its position, shape, something like this. Right? This is for T equal to T1. Now if we multiply both of them, which will give also an E. Multiplication of E times 9/2. How it will look like? It will be something like this. And then equal to 0. This for T equal to 0 Kelvin. And for other temperature, this will be like, and then variation. So basically, electron which are very close to the Fermi level, Fermi energy, they are actually contributing heat transfer or something, so which actually take participate, which are close to the Fermi level. Right? Now moving forward, we know that energy per particle is actually given as where Kb is the Boltzmann constant, right? And at Fermi temperature, energy will be the same, just since this time the temperature will be Fermi temperature, right? At the Fermi value, the d of E f actually will be actually from the equation E by E cube upon 4 2m square pi square 3/2 EF 1/2, and energy of occupied state, it will be E cube upon 6 2m square pi square 3/2, and E of f to the power 3/2. Right? Now, what we do, let's divide these two equations and divide d of E of f upon n of E of f. It will be actually 3/2 1 upon EF. So density of state, the energy EF is P by 2 density of occupied state upon EF. Now, number of electrons participating at a given temperature, or number of electrons participating at a given temperature is actually will be multiply with energy kBT. It will be, if we put this d of f equation here, it will be c by 2 n e of f upon e f kBT. Now, since only one electron are actually can occupy only one state, so n of e of f actually is the total number of electrons that are there. So this can be rewritten as p by 2. Let's call it NP on EF kBT. Okay. So these are the number of electrons participating at a given temperature. Now the gain in energy because of this temperature, gain in energy E will be actually participating electron, which was EF kB2, and multiply with 3 by 2 kBT, which was kinetic energy. Right, so it will become 9 by 4 NT upon EF kB square upon T square. And if you put the value of EF, which was kBT, that will be 9 by 4 NT kB square T square upon kBT of. So this energy E will be 9 by 4 NT kB T square upon EF. And very previously we know the specific heat capacity at constant value. EFP is actually differentiation at constant value with respect to temperatures. So if we differentiate, what we will get is 9 by 2 NT kB upon EF. Right? So this is the formula for specific heat capacity by using Drude-Sommerfeld model. And the formula estimated with only with a Drude model when electron was considered as a classical particle was NT kB. This was from Drude model. And as we have also discussed or mentioned multiple times that it is actually overestimating. Drude model was overestimating the specific capacity by a factor of or order of 2. Right? Now, in the Drude-Sommerfeld model, there was a ratio between T and TF, which actually take care of this one. This is the new introduced terms when come from when we consider it electron as a quantum mechanical particles. Now, at a room temperature, the value of T is around 300 Kelvin, and the value of TF is actually around 28,000 Kelvin. Yes, it is right. The value of TF, the temperature of electron, that Fermi temperature is actually at room temperature is 28,000. Why it is so? Because basically there are millions of electrons are there, right? And we mentioned only few electrons actually participate. So those electron has a very high Fermi temperature, it's at 28,000. But when we measure the temperature, we are actually measuring overall average temperature, which consider all the temperature of all the electrons. When we average out, that is what we are measuring, which come out to be less. And if we divide T by TF, if we divide, it come out to 10 to the power around this much for that. So basically, Drude order was overestimating it to be by a factor of 10 to the power 2 because there was no terms U upon TF. Using Dom's Drude-Sommerfeld model, it actually take care of this. This was the beauty of Drude-Sommerfeld model.